Hello, my name is Ethan Chinnis, and this is Lab 6, Magnetic Molasses. The purpose of this lab was to analyze a B field and the current produced by the falling magnet through the aluminum tube, and then the force generated by which it causes it to fall slower. And then we created a computational model to represent this, and the results were that the real-world time was 1.41 seconds, and the computational time ended up being a little faster at 1.39. The physics principles in this lab were Faraday's law, first of all, which is that EMF it does equal to this E non-Coulombic, but for the purpose of this lab, it's the change in flux over time. And the Biot-Savart law, which is the change in B, which is used to calculate the magnetic flux change, is equal to IDL, which is mu cross R over R squared. And then also, of course, Newton's second law, force is equal to mass times acceleration for the gravity. And in the experiment, here's the experiment right here.
Go.
The magnet fit the tube, falls through. System's the bar magnet surrounding the aluminum tube, air, and earth. And the experimental times, we did 5 trials, which you can see all the times here, and the average 1.41 seconds. And then we made code for this lab. This is the constants that already came with the code. U/4 pi resistivity of aluminum and G. The mass of the magnet, and the mu mag, which we calculated in the last lab, to be about 4.5. And this is the dimensions of the tube, and then the radius of the tube, which is, let's just calculate our R. And then right here, we calculate the dipole of B, which is the magnetic field, and it's the formula from before. And then we have the magnetic flux, which is the dB, which then can be calculated to get the EMF, and the force that the field is generating on the magnet, causing its acceleration to slow down. And this is the results. We had a diagram of the magnet here with the red and blue, and it would fall through to the bottom, and you can see that in the GlowScript code, which is in the description. And then this is the graphic created with 1.39 seconds. And the graph can be interpreted as right here is it's entering. This is the force of gravity is greater than the force from the B field, and it causes it to go down fairly quickly, but then it enters the tube, and they sort of equal each other pretty much, and cause the acceleration to be very slow or constant compared to what it was before. And then here's when it goes and exits the tube, it falls back down again faster, and then it hits the table. And the red and blue are the currents. So the red is counterclockwise and blue is clockwise. That's due to Lenz's law. And if you were to flip the magnet, these two would flip because you'd flip the north and south poles entering the tube. And the time is slightly faster in the simulation here, 1.39 seconds compared to the 1.41 from the real world experiment. That's because we neglect air resistance, and also there could be some human error, which we'll discuss in a minute. But the air resistance would cause it to fall slightly slower in real life. And the plot shape, of course, before force of gravity is greater than F of B entering and exiting, but they about equal each other, which causes acceleration to decrease and slow down. So the sources of error for this lab is that there's air resistance. We neglected air resistance, so the lab data is slightly off from the real world application. And there also could be some error from the previous labs, such as like humidity and such, or any human error from the last lab carried over to this experiment because we use the same mu mag, more so the human error, which is very similar, which in the last lab was just calculating the mu mag, getting everything measured correctly. And then there's also human error in this lab, which is error in timing, in the video it should be pretty accurate because we used the video and calculated the time, but there could be still some error. And also measuring the tube, which before is in our constants, 0.5 meters, and the width and the radius of the aluminum foil could be slightly off from what it actually is. And also making the magnet drop steadily without hitting the sides of the tube, because that'll cause some friction and cause it to slow even more than it should. But in a perfect world, in our experiment, our code here, we have it not touching the tube at all. And the what ifs, if the aluminum resistivity was close to 0, since V is equal to IR, that's Ohm's law, the current would have to be much stronger to equal the EMF that the B field produces, which is the volts. So that means if the current's much higher, it'll have much more force and be slowing even more than it would now with the aluminum's resistivity. And if there were holes in the tube, less rings of current would be produced by the B field around the thing, because there's holes in it, obviously. So if less rings of current are produced, the magnet the total B field would be weaker, and the magnet would fall faster because it's not able to produce as much force to slow down. And that is all.